So,
I got the webcam audio going.
oh good, all right. Hello everyone on the live stream as well. We're just talking about the YouTube channel here, and we are just about to get started with the main presentation for today. That is ultimately a review of that event and some of the data that we captured, the high resolution data that you most haven't seen yet. So let's go ahead and get started with the show. There it is. So Lunar Eclipse, and my name is Jeremy, and I was the Livestream astronomer on that program that day, and it was really exciting. I mean, some of the viewers I'm sure are tuning in now on YouTube, and we had viewers from across the world asking questions and interacting. I think our peak during that stream at one time was about 25,000, so we were really excited about that. Okay, so some things we're going to discuss today. Why did it not? Oh, there we go. We're going to talk about the spring 2022 lunar eclipse, and there's a reason I'm specifying spring there. We'll find out. Then we're going to do an overview of that event, how it all played out. We're going to do some behind the scenes on the equipment, and some behind the scenes on the software. Then I have a little bit of a gallery to show you, and I might even take you into the full photo album to see all the raw data. But I have a few select shots that I definitely wanted to specify. We'll see how we're doing on time and whether we jump into that. Then we have the lunar eclipse time-lapse, and that's that 1.5-minute video. I have that baked into the presentation here. We'll take a look at it, and afterwards we'll go into how we put it together, how fast it actually is. And then we have a lunar eclipse preview for the next one. We'll find out when the next lunar eclipse is. So if you missed this one, there's another opportunity this year, perhaps a little bit less convenient though. Okay, so the total lunar eclipse for spring 2022. And this is from May 15th to the 16th. So it did transition into the next day during this. And let's see what we have. So the timeline for this event, we did preview this during our Spring Skies program, which was also streamed out. And it was about 5 hours stream covering almost the entirety of the event. We did stop a little early because I was getting a little tired at that point at 2 a.m. So the tail end of the event we'll talk about here and why it's not as important. So here's the 7 stages of the total lunar eclipse. We have at 9:32 p.m. was the start of what's called the penumbral. There's a penumbral, there's the umbral eclipse, which is also called the partial. And then while you're in the umbral eclipse, at least for this one, we entered totality. And that's among the best moments in the eclipse event. Now off to the right-hand side, you see a diagram that shows you how these eclipses work. There's the sun. The sun provides our light in the solar system. So that's what gives us daytime. And when we're in the Earth's shadow, that's nighttime. So we're heading into nighttime now as we enter the Earth's shadow. And that shadow is called the umbra. So every day we enter the Earth's umbra. And that's the very dark, harsh shadow. If you look around the room, you see the very dark shadows in the room. That's the umbra. The penumbra, again, if you look out around the room, you'll see some diffuse shadows. These very, they're not super dark. They're just darken, in this case, the ground. If you look at the chairs, they darken the ground just a tad. It's like an out-of-focus blurred shadow. That's the penumbra. And the penumbra part of the eclipse, which is that start at 9:30, doesn't change things too much. There's a slight dimming of the moon, but it's not very noticeable until you approach the start of the partial eclipse at around 10:30 in this case. Now 11:30 is where things got really exciting, because at that point we're completely in the umbra of the Earth. The moon went completely dark, except for some glow, some red glow. And you may have heard of a total lunar eclipse referred to as the red moon or the blood moon. And that's what we call a total eclipse. And you can see the umbra there is shown as a reddish color. Now, at midnight or so, we entered maximum eclipse, and that's when the moon is as far through the umbra. It's sort of its midpoint. It's in the darkest zone of the umbra. And then the end of the total eclipse, when it started brightening up again, was at almost 1 o'clock in the morning. And we kept going until the end of the partial eclipse. And then I decided to call it quits at about 2 a.m. or so. Okay. So here's a little video from NASA that shows you the path of the moon during this event. Those that watched the live stream, we had this going during the preview. So just to give you a sense of where this would be going, how it would pass through the umbra, it gives you some nice timestamps there too. So you can see in the penumbra, there's not much change, but once you enter the umbra, that smallest circle, there it goes. And you'll notice it turned red as you entered the umbra. And that's, again, that red moon, or the blood moon they call it. There we just passed maximum eclipse. And like we said, the totality ended just towards 1 in the morning, and it brightened back up. So eclipses like this, lunar eclipses, can only happen during a full moon, but they don't happen every full moon. Full moon's coming up next week, and it's not going to be a lunar eclipse. One nice thing about them, though, is that as long as you can see the moon during the timeline of this event, you can watch a lunar eclipse. You don't have to be in a specific spot on Earth to see totality like during a solar eclipse. Solar eclipse is effectively the opposite of this event. Solar eclipses occur when you have the moon in between the sun and the Earth. This lunar eclipse is when the Earth is in between the sun and the moon. And that syncs up to full moon, whereas solar eclipse syncs up to new moon. All right. So I wanted to talk and review the live stream, just to show you that we did try and make it as convenient as possible to watch as a replay. And here it is. We have these nice windows laid out, so you saw a live camera view from one of our telescopes. And we'll see more about that when we do the behind the scenes. And then I was there answering questions with my webcam feed, and we had a countdown to totality early on in the stream, which we eventually replaced with a preview of some shots we took with the camera. Because this was a video effectively, and you're limited on how the quality when you're taking a live video, especially of celestial objects. So capturing a single frame, can get rid of a lot of noise, and that was the benefit of doing the frame previews, which I have an example here. So we were getting the live video here of the event, and then over here we got the frame, a single frame taken from the camera. And I don't know where I was in that in that moment, but I'm not in the camera feed. We started with an introduction, and you see YouTube has this really nice feature where you can break things into chapters. So we broke them up, and you can see where there's the penumbral eclipse over here. There's a chapter for partial eclipse, chapter for totality, and then we go back to partial, and finally end with a bit of the penumbral and some concluding thoughts. And all that time we were asking some, people were asking great questions. We were having some great conversations, not only related to, we keep them very freeform, they weren't just related to the lunar eclipse. If someone had a general question about astronomy or telescopes or the cameras and so forth, the equipment, we were happy to answer all of those. Okay, so again, you can go back and watch that.
Live stream.
And now we'll go into a bit of the behind the scenes of the equipment. And this is something I had a limited ability to show everyone during the stream. So I thought we'd go over some of it now. I think we have a good sense of the event at this point, so let's find out how we actually put this together. So the equipment we used, and this is on the right-hand side, you're seeing a shot of some of it. We have our telescope, one of the scopes that you have maybe seen here already, or you will see later tonight, is the 6-inch f12 refractor. We'll go into a little more detail about that one. It's stationed on an equatorial mount. Again, we'll discuss that a little bit. And then the camera we used was a Sony a7 III with what's called a T- adapter. All right, so there's a picture of the 6-inch, and again, those that are visiting in person will see it. Those on the stream, this is what it looks like. And let's talk about some of the specs on this, the specifications. It's a refractor, and refractors use lenses. Just like a magnifying glass or the lenses in my glasses, it brings things into focus and magnifies using lenses. Ultimately, a pair of lenses, a large primary lens, and then an eyepiece, which is a much smaller lens. All right, now there's the aperture of this scope, and that's the diameter or the width of the tube, is 150 millimeters, or that equates to about 6 inches. So that's where this telescope gets its name. The focal length, this is how long from roughly from eyepiece to primary lens, how long is the telescope? And it's about 1,800 millimeters. And that's also where you see that f12 ratio. This means it's that very long focal length means you can magnify and really push that magnification quite a bit. The official name of this is, I think, the Astrophysics Superplanetary Refractor is what the company termed it. And that's in part because you can really zoom in on the planets, really push on a nice clear dark night when the planets come around this fall, and especially Mars when we go on close approach in the winter. We'll use this one for sure. This is brilliant for those bright planets out there. And then there's that equatorial motorized mount. Equatorial mounts are designed to follow the rotation of the Earth so that you can track objects. Now, if it's unmotorized, you have to guide it along. It's you will have it synced to the moon, for instance. At first, you'll line everything up, but after that point, it's not motorized, so you'll have to adjust it, but you only have to move it along one axis as the night goes on. So that's handy, but if you motorize it, then it's going to start tracking for you. And you can adjust it to different objects. You can adjust it to the stellar background, so you're following stars. Or you can adjust it to objects like the moon. And that's important because for us, we can sync it up to the moon, because the moon will move eastward as the night goes on, relative to the stellar background. So it'll trace a little bit, and in fact, we'll see that later. We'll see that effect when we watch our time-lapse. All right, so that's the telescope. The camera is a Sony a7 III. It's a full-frame mirrorless. Full frame just means it hits that 35 millimeter film standard. So that's, if you ever see the term full frame, that's all that means. It's a really big sensor compared to a crop sensor that you might see on a traditional DSLR. So this is great for capturing as much data as possible, as information as possible that comes through the telescope. And it's hooked up with what's called a T- adapter. And let me show you these two things here. Now, this is the camera. Now, right now it has a lens on it, like you normally would expect a camera to have. Let me bring this around this way. So it has a lens on it. This is ready to go and take pictures outside. It's a pretty wide field lens too, so this would not be good for imaging the lunar eclipse if you want to see any detail set up as is right now. What you do during an eclipse like this, and as long as you have a big telescope, but you don't actually, to be honest, you really don't even need a big telescope. You just need something that can fit a camera like this. Big telescopes are good for getting more detail, but use what you have is what I say. So what we end up doing is you take off the lens, the primary lens, like so. Let's put that down like this. And you attach this T- adapter. And you snap it on just like the lens, and now this is ready to go to fit into the telescope, like an eyepiece. So you just snap this in. There's a retention screw that holds our eyepieces in. You use that same system for this, and you focus it just like an eyepiece. You use the focuser adjustment on the scope, and it's ready to go. Now, to protect my sensor, because there's no telescope to protect it today, I'm going to, you can see the full frame sensor in there too, by the way. There's the camera there as well. To protect my sensor, the T- adapter doesn't have any sort of protection like a lens offers. So I'm going to put the lens back on. And those in the live stream, there's the T- adapter that we hooked up to the camera. All right, there we go. And we call this, when it's hooked up to the telescope, a prime focus setup. You're achieving prime focus, and that means all of the light that's coming through the telescope is focused onto the camera's sensor. So you get a clear image, and you're getting as much information from the scope as possible. Now, altogether, I want to show you the field of view that we got, and actually we're seeing it now. Drew, could we turn this front light on? Thanks. So there's our field of view, and I found at a certain level, magnification really doesn't give us a great idea of how we see these objects. Like, okay, what does 120 times actually look like? How do we visualize that? I find field of view makes more sense. So the human eye, this is an approximation, has a field of view of about 135 degrees in your horizontal and about 180 degrees in your vertical. So that's our angular view of the world. We see it as a cone, our vision's as a cone. Now the equipment with the camera and the telescope, when it's all hooked up together, gives us the field of view you're seeing off to the right there with respect to the moon. So that's 1 degree. These are angular measurements. 1 degree by 3/4 of a degree. That's a very narrow field of view, but we need narrow field of views to observe objects that are small in the sky. And the moon is a large object relative to other things, but it's still pretty small. The moon is about 1/2 degree. And if you look here, that should make some sense. The moon is filling up about half of the horizontal in this image. So, best way to think about this, to get an even better visual on it, your pinky at arm's length is about 1 degree in width. Again, we're talking degrees as an angular distance, not as a temperature. So it's about 1 degree in width, and your pinky nail is about the size of the moon, at least in diameter. So that gives you an idea of what this camera and the scope was able to do. When you hold it up, that's the spot, the field of view that we were looking at in the sky. We really pushed the magnification and zoomed in. So that was ultimately what we were seeing in our camera. And there are some great calculators and measurements that you can use on the web that allow you to estimate this for your equipment. So if you have, say, a 70 millimeter telescope with a set focal length, you can input that information along with your camera, and you can get a sense of the field of view it will show. And you can even select different celestial objects. In fact, I think I have that page loaded up. Why don't I just show rather than tell? Yeah, there we go. This is Astronomy Tools. Great place to go. And like I said, they have a bunch of calculators, not just for field of view measurements, but magnification, focal length. And you have visual mode where you're using an eyepiece, or imaging mode where you're using a camera. So eyepieces are where you would be looking directly through it. And you can choose a scope. Now, some of these, maybe your scope is in this giant list. Ours was not, so I had to put the data in. And you can choose your camera. Now, they have a pretty solid list of cameras, so you should be able to find yours. I was able to find mine. And then, altogether, when you select the moon or a planet, you get your field of view right down here. It shows you exactly what you'll see and how big the object will be. So, for instance, if I was to choose Mars in this field of view instead of the moon, do you even see it in there? That's because planets, right, they're even smaller than the moon, way, way, way smaller. And I would need to use a different camera system if I wanted to see more detail for Mars. Something with a much, much smaller sensor that still has a good enough resolution that it can pick up the details on the planet. So yeah, that's like maybe a couple of pixels wide on my screen. I don't even know if it's showing up there at all. So, but here's the sun. The sun is not too far off from the moon in size. Much bigger object, right? So a great tool to use. That's Astronomy Tools if you're curious to go see what your equipment can do. Okay. All right, so we did got into some detail on the major equipment. Now we'll talk a little bit on the software that we used. So really there's two major things that I need when I run these live streams. And that is, one of them we're using right now is called OBS. And that's an open broadcaster software, OBS Studio. Great tool. I'll give you a quick glimpse at that in a moment. And then there's something called, now this is specific to my camera. Other cameras, other brands will have different software like this for DSLR and mirrorless type cameras. It's called Sony Imaging Edge Desktop, and I'll show you that too, at least as much as I can. So let's have a look quickly at OBS. Just right here. Oops. And there we go. So this is, I don't stream off of this computer, so it's there's no it's not prepped at all for a live stream, but it is demonstrating how it captures a display. You can see it's like a mirror world. Anyone seen Doctor Strange or something? That's not too far off. But there you go. So you can see it's an endless portal of displays, because it's just mirroring again on top of each other. It's mirroring OBS on top of just the overall display. So it's infinite. But it allows you to capture displays, audio, and mix it all together and stream. So it's that's what we ultimately use for sending out the signal. Really powerful, and it's free as well. It's an open piece of software. So it gets modified. You can put plugins in. It's very useful. Now the other one has Sony Imaging Edge Desktop, and this has 3 nice features on it. There's a remote feature. That's ultimately what I use to pull the video from the camera. Let's just see if it maybe will work now. No, you see there's some conflict on my computer that the camera's already found a place to go rather than on the remote. So like I said, I don't use this computer for that setup, but the remote allows you to control the different functions of the camera, so I can adjust exposure and how much light is being let through. It's very powerful. Basically, all the controls that are on the camera are available in this software. And then you also get a mirrored version of the monitor. So the monitor that you see on the back of the camera, like most have, it takes that video feed and pushes it over a USB cable to the computer so that I can view it. And the nice part about that is it doesn't require a high-end USB cable. You can just use USB, what they call USB 2, and that means for us especially, in some cases we need to use really, really long cables, and USB 2 works great for that. So that's what we ultimately connect it up to, so we can venture into any of our telescopes. The viewer, I think, did work, and the viewer is where whatever you capture from the remote, you get to see the preview of it here. And that's how we captured that small window in the live stream. And then there is, this I don't use too often, I use other editing apps, but they do include a way to edit your photos if you like. So that's really all it took. And of course, you know, our telescopes and everything combined, we were able to stream this out. Let's go back in. So we did that. Now we'll venture into the gallery to see what the full resolution frames that we captured look like. And we posted one to, at least one I think, to Facebook. And we also had a lot of submissions on Facebook where people shared their photos with us that they took on their phone, or even a camera like this with a nice lens. So those are still up on our post feed. So if you want to check those out, you're welcome to. Just go to Kopernik's Facebook page and you'll see them. Okay, so here's the first one. This is when the partial eclipse began, or thereabouts, at around 10:35. This was with the Sony camera and the telescope. And for those that are photographers, I included some of what they call metadata, what the settings were on the camera. So ISO is a measure of the sensor's sensitivity to light. This camera, I think, goes up to 100,000. I'm not sure how useful that is, but 250 is a relatively low number. And the lower you go, the less noise there will be, but the darker the image. So you can crank that up to get more light in, but it'll get noisier and noisier as you push that setting. Then down below, this is 1/100 seconds. And that's how long it took to collect the light. So it was very quick. And that should make sense because the moon's super bright when it's not in eclipse. Even when you have some shadowing going on there during partial eclipse, you still have a lot of bright moonlight. So you have to do a quick shot for that. And you'll find as we head further into these images, like this one, it's impossible to expose to the very harsh shadow you're getting from the umbra, the very dark shadow, and the bright moonlight on the other side of that. you really have to take two different pictures to try and match both of those light levels. So you could get detail like you see on this image, where you have all that bright moonlight, but if I want to capture the shadow, I have to crank the light settings up. You can see I was able to leave my ISO the same, so not as much noise there, but I brought my exposure, my shutter speed up to 4 seconds from 1/100th seconds. So this really collected a lot of light from the shadow, but too much light from the moonlight. All right, then we have a nice, just when the partial eclipse ended, 11:23, totality started at 11:29. Again, the ISO setting's the same. I did a 2-second shot here to try and capture any little detail on the rim of where that light was fading. And you're getting a little bit of a red color. Not much. I would have to bump up the exposure to get some more of that. And there we go. So this is when we crank that up a bit. This was a little after the total eclipse began, at 11:54. Now we brought that sensitivity way up. So we didn't have to run as long of a shutter speed. So there's a balance here that you can play with. There's still not too much noise on this. Now what is very cool about this shot, I think, is you can see a star right there. And that star is called HR 5756. That's a wonderful little name, isn't it? This is an unnamed, unnamed star. It's cataloged because it's just too dim, really, to see with your eye much. Yeah, or at least make out like it's not one of the brightest stars in the sky. Those ones get the names. This one gets a catalog. What is cool about it, though, is one, that the moon was dark enough that we could see it around it. Usually you can't capture stars around the moon during full moon, especially because it's too bright. But in this case, we captured this HR 5756 because the moon was so dark. And if you look carefully, I'm not sure how it's coming along on the projector, but on my screen up front, I can see that there's 2 stars there. You see that? This makes it a binary star. Now, it's not necessarily a true binary. I was trying to get as much research out of it as I could, but from what I gathered, it's not a true binary, of course. Usually those end up being very close to each other, almost imperceptibly close. But they are very close in the sky, so they end up being very interesting to look at through telescopes from our viewpoint here on Earth. There are true binary stars out there that are in orbit around each other, like planets orbit around the sun. But this one's not an example of that. I did not capture, because the moon did move in front of that star, I did not capture what's called the occultation. I had to go run to the telescope to adjust something, and during that time, I lost that opportunity. But the moon did pass in front, so you would see one star disappear and then the next, which would have been pretty a cool sight. You can go back in the stream and watch that happen, I'm sure. Okay, now here's a cool shot, I think. You can see towards the upper right, that is the tube of the telescope. And you see the window out of our dome. And so that's what the telescope is looking through, and I'm sure you can spot the lunar eclipse as well. Now, this was a very wide shot. Now, you may ask, okay, your camera's hooked up to the telescope. What did you use to take this image? Well, a phone. Phones have gotten so sensitive, and they do so much live processing on the data that they're capturing that they can now take pictures of the night sky and also adjust to not only are you adjusting to the darkness of the night sky, the starlight is somewhat bright to our eye, but to a camera, especially a camera with such a small little sensor on it, that's not bright at all. I mean, you go back 10 years, there's no way you could have gotten a picture like this.
Actually, Jeremy, if I can
interject here?
Sure.
For those that are here, after the end of the show, I have a picture of my phone that I took of Comet Neowise right out here in the parking lot. So at the end, if you're interested, come on up and I'll show you the picture of the comet picture that I took. Then it's clear that it's a comet. You know.
Yeah, that'd be great. And in fact, we could, if the skies are clear, we could, for those that are here, we could demo how you take those photos, and we could all try it together. That's an option. Yeah, this was taken on an iPhone. This was the total eclipse, actually earlier than the previous picture. Now the settings are a little weird because these are predetermined for you, at least in the base camera app. But I found that the default camera app works best for wide shots like this, where you're not changing those settings. The phone decides what's best. So you're able to see this though. After you take the picture, you're able to see what the camera chose. So with such a small sensor, you need to really crank that sensitivity up. So that's why it's 3200. There's so many lenses on our phones nowadays. So they chose this one chose the 26 millimeter lens. There's a variety on here. This is I think just the base lens, the 1x lens you'd call it. Now the shutter speed is where it gets weird, where it says 2 seconds, but when you're taking this image, when I took this image, I had to hold the camera still, aimed out the dome, for 10 seconds. So what I imagine happened, as I understand at least how the processing works, as it puts this photo together, is it took 5 2-second images, and then it stacked them and pulled the best data from each of them. That's something we do with astrophotos all the time with various pieces of software. But what's cool is that now phones are doing that. Their processors are good enough that they're doing that all at once. Like this happened, I got to see this picture in about a second as it processed it. So it's incredibly powerful applications that we have on our smartphones and the actual cameras themselves. Okay. Now, I think this one's my favorite shot. And there's a bit of processing, but I will say there's no, I'll show you the settings I used. There's no adjustments to saturation, from what I recall. So this is really just playing with contrast and brightness to get this wonderful gradient of colors across the moon. It isn't necessarily natural, I would say, though. It doesn't quite, it's a little bit past natural. I'm getting into a little bit more of, I wanted to use it as a wallpaper on my phone. So I tweaked the settings a little bit. But the ISO, this is from the telescope and camera again, the Sony camera. This was a 15-second exposure. So I was able to collect a lot of detail, especially in the very dark area in the north of the moon there. So we're really capturing a lot of the craters. Crater Tycho, the big crater in the lower right. That looks nice and detailed. So this was probably the best one I captured, and that was during the close to the maximum eclipse. So I'll quickly show you the album of all the images we captured that day. You see some of them I was trying to capture the shadow. Others I was capturing the bright moonlight. And this is all chronological. So I may consider putting together a more staggered time-lapse rather than a smooth one, so that we can see it play out as high-resolution photos rather than the noisy video that we did capture.
Jeremy?
Yes?
Some of those remind me of the diamond ring effect you get during the solar eclipse.
Oh, I don't know if I'm familiar with that. What happens during that?
The diamond ring effect?
Yeah. At least I haven't heard it referred to as that.
Okay, like, take the second one in,
Second one
That
in.
one there.
This one.
okay? Well, that would be like the diamond in the real bright part, and then you can see sort of like the outer edge, which is like the ring.
Oh, okay. Yeah. Okay, I can see that.
On
Yep.
solar eclipse, when you get something like that, which is a little brighter,
hmm
they call it the diamond ring effect.
Oh, okay. So that's when you're getting some just maybe a tad bit of sunlight on the edge. Okay.
Right, and then
Yep.
you see like a little ring around it.
Very
They
cool.
call it the diamond ring effect.
Okay, that's kind of cool. We're getting that analogous to the solar eclipse. So then we even have the wide field shots in here. This one, I think it's not cropped. I think that one came from the telephoto lens on the phone. It's a little bit noisy though. And we saw examples of these pictures earlier, but I want to re-emphasize this one because you can see the system in action. You see the camera hooked to the back of the telescope with that T adapter we saw. You actually see the monitor. And again, that feed that we're seeing there on that monitor is what was streamed out. We pulled that direct feed from the camera as video and we streamed it out for the live stream. And then you see the telescope pointed out the dome, and finally you see the eclipse. So you get to see the whole stack of equipment minus the computer, but I don't think that's as interesting. So I think the main optical equipment is what's cool here. All right, let's go out and see if there's any other ones I wanted to mention. Here's one more like that. Again, where you can actually, that monitor is even clearer in that image. That's kind of nice. And then, yeah, the eclipse wrapped up. Oh, and then one thing I wanted to include too. So this was the last bit of the penumbral eclipse that we imaged before I wrapped up for the night. I packed up everything in the domes, and then that's what I saw outside. So we started with clouds during this event. Hazy clouds, but it was still a little bit cloudy just before the eclipse began. We had clear skies throughout the entire major event, especially through totality. I don't think it clouded up once that I can recall. And then when I left, we got clouds. So we had our window, and I'm so glad it worked out. It's rare for it to work like that in Binghamton. Usually it's the other way around. All right. Now, one last thing I'll mention with the photos. I've talked about how we have, here's a good example. We have a capture of the shadow and then a capture of the moonlight. And one thing I did for the November partial eclipse, it was not a total eclipse. It got very close, but it wasn't a complete, we never reached totality. I have that album here. What I was able to do for this one is I had captured the moonlight where it was nice and bright. I captured that information. This was as close as we got to maximum eclipse for us. The true maximum was a little bit less light, less moonlight, but that it clouded up at a certain point for us during that stream. So I captured the moonlight there, and then I captured the shadow. Again, you see it's overexposed, but one thing I did in processing is I put them together. I took the information from the bright side of the moon and the information from the umbral eclipse. And when you stack them together, you get a complete moon, all in one. And I really like the gradient in this one too. It's less full orange and more, you're going from the red to the orange to the yellow, the gray, and then the white. So I like that gradient quite a bit. That was the same setup, by the way, same camera and telescope. So I'll probably try something similar with some of the partial eclipse captures that I got too. All right. Now let's get into, quit on me, there we go. Let's get into the lunar eclipse time-lapse. So I have the video here, we'll watch. This is the eclipse in a minute, more or less. So again, I mentioned, started with some hazy clouds there. Then it cleared up. You get to see the umbral shadow crawl across the moon. And totality begins. They crank up the light levels and oh yes, thanks. The stars, the stellar background there, that double star, that was the occultation that I talked about. So that bright star is the double star. There's the occultation. And again, this red color I haven't mentioned yet is coming from our atmosphere. The red color is there for the same reason that we have pink skies at night and in the morning. It's just that indirect sunlight, that glow from our atmosphere coming from the sun, that's getting pushed to the moon. So it's not, the moon's not glowing, it's really indirect sunlight. There we go, the partial eclipse is about to wrap up. Did you see those blacked out periods in the video? Those moments where we didn't have a frame. I included those for a very good reason, and I think I can show it to you. I want to wrap up in a few minutes here, but this is what I used to put the time-lapse together. It's just a movie editing software. And you can actually scrub through it and hear the audio. But I'm going to turn that off for now. Now this is the video you just watched, and I exported that. Now, if we just looked at the base file, I didn't do any edits to this one yet. You can see the footage. Oops. And as we scrub through, you can see the clouds moving in front. Let's see if we can shorten this up a bit. There we go. But you can see occasionally I have PC data, like PC screens, showing up here or there that I had to cut out. So that would be an example of a black screen. But you can really see, look at that shadow move across when you scrub through fast. And there's occasional points where it, like this frame here, that was no good. I tossed that one for the sake of putting together at least a time lapse that was of similar exposure. And there we go. It concludes. So there's a couple of frames that I cut out to smooth things out, and I did my best to stabilize the video by eye. The stabilization software didn't work super great for this purpose. So I just tried to adjust it as best I could. And that's how we put together the time lapse. So I'll show you one last thing back here. If we look at the speed, there we go. So the clip, if you look, we increased the speed of the video by 16,000%, which is about 160 times. So you really you took those 5 hours and sped it up 160 times. That's how we got it down to that minute and a half. Okay. And we don't have to watch again. Like I said, that video is available on YouTube if you want to watch it yourself. Okay, so that really wraps up our discussion on the last eclipse. Last couple minutes here, I want to take a moment to talk about the next eclipse. because I specified last one was spring 2022. There is another one coming up this fall, and it is a total eclipse, unlike last fall's only partial. So this was November, and this will be November 8th, which is just after daylight saving time ends. And here's the timeline, same layout as we had before. Starts, now here's the kicker, I guess. You see the time there? Yeah, this one, the last one started at 9 p.m. For us here on the east coast of the U.S., it starts at 3:02 a.m. So, not super convenient there. You have the 7 stages of the eclipse again laid out. I won't go through each time. I think we have a good understanding of that. Now you may ask though, why is it red at the bottom? It's not because of the red moon. It means we can't see those stages of the eclipse because the moon's going to set below our horizon at that point. If you're on the west coast, you can see, I believe you can see the entirety of this event, the west coast of the U.S. But it's still not super convenient for them either because they'll have to be up until I think 2 a.m. still to get a good complete version of the eclipse on their side. But this is great because I know we had some people tuning in from across the world, like I said, for that live stream, and they weren't really able to see this one. It wasn't the timing wasn't right for it. So like those in Australia and Asia were able to. They will be able to see this one at a nice convenient hour. So this is great for the other side of the world this time around. And it's nice though that we can still see it. If you wanted to stay up late and watch this one, you could. So look out for it.
Or get up early.
Or get up early, yes. Whether you're a night owl or an early bird. So there's that diagram again. Now, I wanted to give at least a little bit of a tease of what's to come for our observing live streams. Because there are that's the next big astronomical event that will happen. No solar eclipses or anything this year. We did have a solar eclipse a partial solar eclipse last June. And I went up to Oneonta Shores to see that one. We couldn't. I didn't trust our horizon here. It was going to be a very low 10-degree altitude event, just coming up as the sun rose. So we have too many trees to make that happen. So I made sure that I had a nice clear horizon to record that stream. But so no solar eclipses this year. Look out for the one in 2024 though. That one's going to be here before you know it. That one's the almost total eclipse in this area. But yeah, what are we planning for this summer? My hope is that in June we can do, towards the end of June, when we don't have a moon, we're heading towards new moon at the end of June. And my hope is that we can do some deep sky tours. That's something I haven't done in a bit. So we'll do some long exposure photography of deep sky objects. Deep sky objects are galaxies, star clusters, nebulae, and they're very dim. And it's near impossible to get good video data from most of those objects. Some of the star clusters you can, but most of them you can't. And to be honest, I'm not sure how much value there is in trying to get video data from them because unlike a lunar eclipse event that's very dynamic, you can almost see it play out with your eye in terms of that shadow crawling across the moon. I'm not sure there's too much value in a video feed of a very static object. I think what's cooler is to capture very high resolution imagery and talk about it. And discuss what we're seeing and the different stars within. It's pretty incredible to see galaxies with your eye for one thing, but then just to collect all that information and put together a photo of a galaxy nice and bright, it's pretty incredible. So that's my goal with June's event. Next up, July. I found a lot of people on the live stream seem to enjoy ambiance, night sky ambiance. So my thought for that one is the Milky Way is going to show up nice and high in the sky coming up this summer and in July. So the cool thing about this camera, and the reason why we were able to capture that eclipse in its red color, is it has a neat setting called brightness monitoring, where you can crank the sensitivity of the sensor way, way up so that you can capture dark objects that are reasonably dark. Deep sky is difficult, like I said, but the lunar eclipse is an example. You can even capture the Milky Way with that setting. So we'll see if we can put together, I'll set up the camera and we'll just have a nice sky. I mean, usually our frogs are chirping outside. I'm sure we'll capture some good natural sounds as well. So it'll just be a nice live stream where you can have it playing in the background. So that's July, and then August is where we finally get the planets. If you've been watching the night sky this spring, you may have asked, where are all the planets? Well, they're all in the morning. You got to wake up pretty early, just before sunrise, to see. Now, it is worth it if you can catch them, because they're all in a nice line in the sky from moving east to south. And I think it's Venus, Mars, so from close to the horizon is Venus, Mars, Jupiter, and Saturn. They're all in a nice line. So it is cool to see them in that state. But especially for our events here at Kopernik, we don't have any planets to look at. But we will when they start rising up in the evening sky for us in August. So we'll definitely be looking at those planets on site through our telescopes, but also we'll plan to observe them, because it's been a while since we've had planets to check out at a nice convenient hour. And I put in parentheses there, maybe the Perseids. I'm not super confident this year because the moon is going to get in our way during the peak. The Perseids are a meteor shower event, and they're usually among the best. I've always enjoyed the show that the Perseids put on. But meteors are tricky because a lot of them are very dim, and the moon is very bright, and it just so happens we're around the full moon during this event, especially during the peak, and in the peak hour, the moon will be out. That's not great for meteor showers. So we'll see what we can do. The thing about Perseids too is ideally you observe them at around 2 o'clock in the morning, when the constellation Perseus is higher in the sky. But that's also, like I said, when the moon is out. So there's a chance. But Jupiter and Saturn are going to be my focus for those. But that's all I have for this program. So we'll do a Q&A session at this point.
Yeah, we do have one question here from the chat on the live stream. Raven Ray asks, are all your images in the visible wavelength range only? And is there any information we can gather from other wavelengths?
Oh, yes, very good. So for our equipment, at least the equipment I had set up for the Eclipse event, it was all visible light. So that's, of course, there's other wavelengths of light our eyes see invisible in the visible wavelength. The James Webb Space Telescope that just launched in December. That's going to finally kick back some pictures here in July. We'll see those for the first time. That sees in infrared, so just super red light, so red that our eyes can't see it, but the cameras on that can. We don't have an infrared telescope or an infrared camera system for our equipment. We do have different filters. For example, the 20-inch telescope has a filter wheel that we can run through and pick up different details. There's something called H-alpha as well. And H-alpha is hydrogen alpha. It picks up a very specific wavelength of light that is really helps you see some solar prominences around the sun. That's very useful. It serves other purposes for deep sky objects as well. You can use H-alpha to pick up, because there's a lot of hydrogen out there. You can use it to pick up different features in nebulae, for instance, that are ultimately made of mostly hydrogen. So there are some possible opportunities there. It's been a while since we've done a solar stream or some solar observing with our H-alpha filter. We've done that in the past, so it might be worth exploring again. Anything else on the chat?
Not currently.
Okay. Any questions in the audience?
Yes.
Yes.
Okay, you mentioned the shower, the meteor showers in August, and you say that so if somebody is looking up and you're seeing the meteor shower, so in actually you're not really seeing the galaxy, you're just seeing the Perseids.
Oh, okay, yeah, good question. So the question was, we're not picking up the audience audio at all, right?
We heard a little bit,
Oh, okay. All right, well then that's good.
but you may
Just reiterate.
summarize it.
So yeah, the question was when you're looking up during the Perseids event, what is it that you're truly seeing? Galaxy, the meteors flying overhead, and in an ideal like last year during the Perseids when we didn't have to worry about the moon. Usually the Perseids can be about 100 meteors per hour in an ideal circumstance. So that's at 2 o'clock in the morning when Perseus is high up in the sky. And a lot of those will be dim, little wisps of light jetting through the sky. Some of them will be very bright fireballs. And that's where you get, the best one I ever saw was at Cherry Springs last year. That's a state park in Pennsylvania. And it probably filled up half the sky from tail to front. And it took about 5 seconds for it to burn out. And it was super bright. I saw my shadow on the ground. It was pretty cool. It had multiple points of brightness. So that's an example of a really bright meteor that you can see during the event. In addition, you could certainly see, like we've been talking about the Milky Way here, all of those objects would be out too. So you'd see the Milky Way stretching across the sky. And what's really cool is sometimes when you're taking photos, you'll capture the Milky Way as well as some meteors flying through your image. So this is a very dynamic event that you can get a lot of cool, see a lot of cool stuff and take pictures of a lot of cool things. Yes, question.
Perseus movie, the Bible chopped off Medusa's head in really bits.
Oh yeah, yes, that is
Repeat that.
yeah, yes, that is the mythology of Perseus. Yep. And we talk a little bit about that when we do our planetarium shows with our portable planetarium, but maybe not that exact story. Any others?
All right, just want to thank you, Jeremy, for yet another outstanding presentation. Just also to let you know that we have people, actually Raven Ray was watching from the Philippines.
Oh, wow.
And he was actually watching your live stream and really appreciated that. We have people from Indiana, from New Jersey, from Toronto, Canada, so...
So the Philippines, you'll probably get a good view of the next eclipse in November, I think. Yeah, so look out for that one. That one is better on the other side.
Right, exactly. All right.
Any other questions?
Gentlemen, I think the sky's still looking pretty good outside?
Yeah.
All right, so we have a rule here that you cannot leave Kopernik until you look through a telescope. So hand me your keys and then you'll get them back after you. Anyway, thank you very much for coming. We'll have another program next weekend. It will be sort of the connection between astronomy and music. And then the weekend after that, actually, I'll be doing one about ham radio and why it's still, it's actually a growing hobby. And so, and then in July, it won't be a live stream, but we'll be doing a program called The Great Telescope Dust Off. So if any of you have any telescopes at home that you haven't used or don't know quite how to use it, bring it up and we'll show you how to use it and make it work for you. So thank you all again for coming tonight, and thanks again, Jeremy, and also thanks for those who are watching on the live stream. We actually have a new live streaming computer which works great when it works. We had some issues this evening with the audio initially, but I think we got that sussed. So take care, be safe, and we'll see you next time.